In modern biology, we're facing this really interesting paradox. We have more data than ever before, but finding the actual story, the real sequence of events in a disease, is somehow getting harder. So today, we're going to look at an incredibly powerful new way to find that one clear signal in a literal mountain of biological noise. Let's dive in. Really think about that for a second. If you're trying to understand how a disease progresses or maybe how a new drug is working, you're not just looking for a single isolated clue. What you're really hunting for is a pattern, a sequence. It's a whole narrative that unfolds step by step inside our own bodies. And the scientific playground where all this happens is a field called metabolomics. It lets scientists measure thousands, and I mean thousands, of tiny molecules, or metabolites, all at the same time. Now, this gives them an incredibly rich, detailed snapshot of what's going on, but wow, it also creates a staggering amount of noise to sift through. So here's how we're going to break it down. We'll start with the data pattern problem itself. Then we'll see why order is so important. We'll introduce this powerful new tool, PLS ROG. And then we'll see it in action with a couple of case studies. One's a bit of a rabbit mystery, the other's on cancer progression. And finally, we'll talk about why this is such a game changer for discovery. All right, so let's get right to the core issue here, what I'm calling the data pattern problem. Our modern tools are so powerful, they can spit out thousands of variables from just one sample. But here's the thing, more data doesn't automatically mean more clarity. Honestly, for a lot of researchers, it feels less like having a map and more like drowning in a huge ocean of disconnected facts. And this feeling of being totally overwhelmed gets even worse when the data you're looking at has a natural sequence to it. This is where you realize that order really, really matters. Because in biology, whether you're talking about a disease getting worse or a patient getting better, that sequence of events isn't just a part of the story, it is the story. And this slide just illustrates the point perfectly. It's one thing to compare unordered groups, right? Like healthy people versus sick people. Simple enough. But it is a completely different and much harder challenge to analyze ordered groups, like the progression from a mild disease to a severe one. The order itself is the insight you're looking for. And this right here is the Achilles heel of so many standard analysis tools. Don't get me wrong, they're great at telling different groups apart, but they treat them like separate, unrelated piles of data. They just don't respect the inherent sequence, which means they can totally jumble the timeline and basically hide the very biological narrative we're trying so hard to find. So, if the standard methods can't see the sequence, what's the answer? Well, this is where we get to introduce PLS-ROG. It's a really clever statistical method designed specifically to solve this jumbled order problem and, you guessed it, put the biological story back into its correct sequence. So the full name is PLS-ROG, which stands for partial least squares with rank order of groups. It's basically an upgrade to a proven statistical method, but it has this one critical addition. It introduces something called a differential penalty. Think of it like a mathematical rule that forces the model to respect the known order of the groups it's looking at. Let me show you how it works in practice. So step one, just like any standard method, it separates the data into distinct groups. But then, and this is the magic part, it applies that special rule, that penalty, which mathematically guides the data. This makes sure that the final result reflects the logical, predefined progression, like from healthy to sick, instead of just treating them as random, unconnected states. Okay, so that's the theory, but let's see how this thing actually performs in the real world. Our first case study is all about a cholesterol treatment in rabbits. Researchers were studying rabbits that had a genetic condition causing super high cholesterol, and they really wanted to see if a specific drug was working at a molecular level. So when they used a standard analysis, they could see a difference between the three groups, the healthy control rabbits, the diseased ones, and the treated ones. But the data was, it was a mess. It didn't show any kind of clear progression from healthy to sick to treated. The whole story was jumbled up. But then, get this. They reanalyzed the exact same data, but this time with PLS-RG. And suddenly, this beautiful, crystal clear story just emerged. You could literally see the progression from the healthy group to the diseased group, and then you could see how the treated group was moving back towards a healthier state. The order made the treatment's effect totally obvious. Now here's what's so cool about this. It wasn't just about making a prettier picture. The actual statistical proof got so much stronger. Just look at uric acid. With the standard method, its connection was basically statistical noise, not significant. But with PLS-ROG, bam, all of a sudden, it's significant. The method didn't just find the pattern, it brought the whole thing into sharp focus. So that rabbit study really shows you the power of finding order. Now let's take that idea and apply it to something even more critical: tracking the progression of human prostate cancer. I mean, this is a perfect example where the stages of a disease have this crucial built-in order that we absolutely need to understand. The original goal here was to find specific molecules, biomarkers, that change as the cancer evolves. From just benign tissue to a localized tumor, and then finally to that really dangerous metastatic disease that spreads through the body. And by applying PLS ROG to that original dataset, the analysis just sliced right through the noise and pinpointed this many metabolites. 94. That is 94 distinct molecules that were shown to be statistically linked to the step-by-step progression of this cancer. That's huge. And the insights they found were just profound. The analysis confirmed that a molecule called sarcosine was a key biomarker, and it even ranked it in the top 5%. But it also uncovered a brand new link to something called fatty acid metabolism. And because PLS-ROG looks at all the stages at once, it revealed this much broader story that was totally missed when researchers were just comparing 2 stages at a time. So from rabbit metabolism all the way to the progression of human cancer, we've seen the proof. What does this all really mean for the future of scientific discovery? Well, this isn't just some minor technical tweak. It's a fundamentally new way to see the stories in our data that have been hiding in plain sight this whole time. So, to wrap it all up, the PLS-RG advantage is pretty clear. It finds more accurate patterns because it was literally built for data that has a natural order. It gives you much stronger statistical proof for your findings, and probably most importantly, it empowers scientists to pull truly meaningful sequential stories out of what was once just overwhelming complexity. And that really leaves us with a fascinating question to think about. Now that we have a tool that can finally respect the natural order of things, whether it's the progression of Alzheimer's or even the development of a child, what other crucial stories, hidden until now, are we about to discover next?